Hello, this is Miraj Patel, and today we're going to be starting Unit 3, and Unit 3 is all about modern atomic theory. And so today we're going to specifically be talking about atomic emission spectrum and the electromagnetic spectrum. And so before we begin talking about the atomic emission spectrum and how it developed the new atomic model, we have to first recall the old models. And so this timeline shows the old models. And so the first model was a Dalton model, and he didn't really specify much about the electrons or nucleus or anything. So he just hypothesized four things about how atoms are indivisible, have specific properties and different atoms, and how they can react and stuff. And then J.J. Thomson discovered negative particles that became called electrons in atoms, and that was because he did a cathode ray experiment where he shot electricity through a cathode ray, and he noticed that they go towards a positive plate. And then Rutherford used a gold foil experiment and figured out that there are nuclei in atoms, and that it's a dense center, and that's what blocks the light and prevents it from going through. And now moving on, Rutherford's model was good and all, but it couldn't explain properties like light color. So, for example, you have this piece of iron here, and you heat it up so hot, and eventually it'll start emitting red light and yellow light. And so, how can this model explain this? Well, it didn't. So they modified the model. And before we talk about how this model works, we have to understand what the atomic emission spectrum is. And I'm sure all of you have heard of the electromagnetic spectrum, which is caused by diffusing white light through a prism, and all the light, all the colors are shown. And so it starts from violet to all the way to red. And the same thing can happen with elements when we put electricity through it. But when you do it with elements, only specific colors will be shown. So only parts of this the continuous spectrum will be shown. So see how there's discrete elements. So you only see this color, this color, this color, this color, this color, this color, this color. You don't see anything else. And this is called atomic emission spectra. And for each element, there's a different pattern of color shown. On this slide, this shows the atomic emission spectra of hydrogen. And so pretty much you get this tube or rod, and you put electricity through the element, and it produces a light. And we have these special goggles that you wear, and you can see these colors. And so for hydrogen, notice how it only shows 4 colors, while helium shows 7 different colors. So for each element it's different, and it shows different parts of the spectrum. And that brings us to the electron orbitals. And the reason why there's an atomic emission spectra for different elements is because these different energy levels. And we'll talk about it in a minute. And so before we begin, there's 2 states, excited state and ground state. And if electrons absorb energy, so if they take in energy, the electrons will become more energized and become excited. So excited state is like high energy. So just think about how when little kids get like a sugar rush and they become so excited. So that's the same thing. They get a lot of energy and get more energy and become excited. And these are higher energy levels if they're in the excited state. So these rings will all be excited states. And the other state is called the ground state. So like after a sugar high, you know how kids, they just like pass out on the floor. So the ground state, you can remember about how kids after sugar high they pass out on the floor or get drowsy. So ground state is like when those kids get drowsy after being excited. So, and this is caused by a release of energy. So if you're gonna lose energy, it has to go somewhere. So this is how atoms, when they get hot, they release light because they're excited and then they release energy in the form of light. And this is called the ground state. So the lowest ring would be the ground state. So this would be the ground state. And in all these examples on the bottom, it shows an excited atom releasing energy as it goes to a ground state or a lower energy level. And notice how it releases energy. And depending on how much it jumps, it releases different amounts of energy. And the energy, or E, released or absorbed is called a quantum, as as electrons change energy levels. So we can actually calculate it, and the amount of energy is called the quantum. And that brings us to a Bohr model. So Niels Bohr was the one that developed this model where electrons are in fixed energy orbitals. And pretty much the model said that electrons only occupy specific fixed orbitals, and pretty much each orbital has a fixed amount of energy. And so if an electron gains energy, it can move to the next orbital. So for example, if we have an atom on the first shell and it gets excited, or energy comes in and absorbs energy, it can move to a higher orbital. And same thing, if an energy is on 5, it can lose energy and move down to 1 or 2 or 3 or 4. And so this is all based off of energy levels. And so pretty much going back to the atomic emission spectra, so when we put electricity through an element, pretty much the atoms are being excited because electricity has a lot of energy. And then when they go back to the ground state, they release energy, and pretty much that is how we get these different light measures, and that is how we see this light. And so that is how it relates to electrons, shells, and the Bohr model. And so here pretty much it shows again, if energy is absorbed, it gets excited. So energy came in and it got excited. And vice versa, if energy is released, that means that the electrons are moving to a ground state. And this is how he discovered, and so discovered the model, so Niels Bohr. And so in 1913 he developed the Bohr model, which is pretty much there's a nucleus in the center and electrons are in specific orbitals, not just randomly like this. And this is how we can figure out chemical properties from these rings. And here's a quick quiz to see what we've learned. So Rutherford's model of an atom could not explain A, any properties of an element, B, the chemical properties of an element, C, the distribution of mass in an atom, or D, the distribution of positive and negative charges in an atom. Well, Rutherford's model, the problem was that it could not describe the certain properties of an atom, and pretty much it couldn't describe chemical properties. And so the answer is B. And it can't be A because it did describe how the nucleus was, like describe, how many protons, neutrons, electrons there were. It did describe the distribution of mass because if you remember from Unit 2, the mass is all in the nucleus. And it did describe the distribution of positive and negative charges, but it couldn't describe chemical properties. So remember, the Rutherford's model did not describe chemical properties as well as the Bohr model could. And question 2, Bohr's model of the atom proposed that electrons are found in A, embedded in a sphere of positive charge, B, in a fixed position surrounding the nucleus, C. In fixed orbits of specific energy, and D. Orbiting the nucleus in a single fixed circular path. Well, if we can look through every answer and eliminate some. So, A. Embedded in a sphere of positive charge. He never said that they're embedded in a sphere. So, you can eliminate A. B. In fixed positions surrounding the nucleus. That's false because they're still orbiting very fast. C. In fixed orbits of specific energy. C sounds somewhat correct, but let's just check D. Orbiting the nucleus in a single fixed circular path. And that also sounds correct, so the answer is C because because D they can change their because they can change their orbitals if they gain energy or not, and so it depends on the energy. So you can eliminate D because it says it's fixed, but it's not fixed because it can slightly change a little bit. And 3, the lines in the emission spectrum of an element are caused by A. The movement of electrons from lower up to higher energy levels. B. The movement of electrons from higher down to lower energy levels. C. The electrons in energy levels in the ground state. Or D. Electron locations of an atom. Well, if you remember, if an element is excited and then it loses energy, it'll move back down to a ground state and release energy. So it can't be A because A says moving from lower to higher, which is absorbing energy, not releasing. So the answer must be B because that's the only one that says that if an atom, moves from higher energy to lower energy, that it will release energy in the form of light. So that's the only one that talks about moving from higher to lower. Okay, question 4. Which transition in an excited hydrogen atom will emit the lowest energy of light? A. E2 to E4, B. E4 to E1, C. E3 to E2, or D. E3 to E4. Well, in order to emit energy, it has to release energy, so it has to move from higher to lower energy levels. And only 2 of these go from higher to lower, so B and C, you're down to B and C because they're the only ones that go from high to low. And E, by the way, is just the level, the energy levels. And so E4 to E1, that is moving down 3, so that's quite a bit of energy. But C is E3 to E2, so that's only 1. So that'll emit less energy. And so the answer is C because it jumps less orbitals. It only jumps 1 orbital, while B skips over 3 and 2, so that's quite a bit of energy. And because it has the lowest amount of energy, it has the longest wavelength, and we'll talk more about wavelengths and energy in the next PowerPoint. And so the next PowerPoint is all about the electromagnetic spectrum. And so like we talked about in the last PowerPoint, as energy is absorbed, electrons move from low to higher energy levels, and this is called the excited state, the upper levels. And the opposite is also true. If energy is released, so like this, it moves from high to low, and this is called the ground state. And then quantum's the amount of energy absorbed or emitted as electrons change energy levels. And so this brings us to electron energy and light. And so I'm sure most of you know this about waves from middle school science. And so the distance between same points on adjacent waves or waves next to each other is the wavelength. So pretty much it's the distance between the same part of a wave. So we can measure from bottom to bottom, we can measure from middle to middle, but as long as you're on the same part of waves next to each other, its wavelength. And there's a second term you need to know, is the number of waves passing a point per unit of time is the frequency. So pretty much the frequency is how many waves pass through at a given amount of time. So in 1 second, if 3 waves pass through, it has a frequency of 3. And if 2 waves pass through, it has a frequency of 2. And these two terms are wavelength and frequency are inversely proportional. So as one gets bigger, so if we have a large wavelength, we have a low frequency, because look how large these waves are. And so it takes many, because it's so long, it takes so much time for even one to pass. But if we have a high frequency, we'll have a lower wavelength. And if both waves travel at the same speed, which has more energy? And we'll talk more about that on the next slide. And so here's the electromagnetic spectrum. I'm sure most of you know this. And a good way to remember all the names of the waves is, think of the sentence, rabbits meet in very, for visible light, unusual, expensive gardens. So again, rabbits meet in very unusual, expensive gardens. And that's how my 8th grade teacher taught us to remember this. And so they stand for radio waves, microwaves, infrared waves, visible light, ultraviolet, X-rays, and gamma rays. And this is from order to weakest to strongest. And of course, to remember visible light, think of Roy G. Biv. And a good way to remember which side is weaker and which side's stronger is, think of infrared and red as together. So infrared and red are next to each other, while ultraviolet down here and violet are next to each other. So infrared is next to red and ultraviolet is next to violet. And as we move from left to right, there's a higher frequency and shorter wavelength. And if it has a higher frequency, like gamma rays, it has more energy than waves with lower frequency. And if it has a longer wavelength, it's weaker. So, and it's important to know that all light or electromagnetic radiation travels at the same speed, and which is the speed of light. And so here's another picture of the electromagnetic spectrum, and this shows the wavelength in context with objects. So the radio waves have a wavelength about buildings, microwaves have a wavelength about humans, and then so on. And notice how gamma rays have such a small wavelength, the size of atomic nuclei, so which is so small compared to the size of buildings. So this gives you about a perception of how much it changes. And this shows an example of things with the particular waves. And when we're learning about electromagnetic radiation, there's these two formulas we need to know, and it's C, or the speed of light, equals wavelength times frequency. And so these formulas will be given on tests, so you don't need to remember any of this, you just need to know how to apply it. And because C, which is always the same, is equal to wavelength times frequency, they always have to equal the same thing, so it's inversely. So if wavelength is high, frequency is low. If frequency is high, wavelength is small. And so they're inverse, so just a good thing to remember on the back of your head. And this formula, E equals H times V. And so E is energy in joules, And h is Planck's constant, which is just this number right here, 6.63 times 10 to the negative 34th, and v is just frequency. And remember, higher frequency is higher energy, and this is a direct correlation. And it's just we just gotta know how to use these formulas to calculate energy from frequency or wavelength. And it's important to know that you can use frequency in both formulas, but you can only use wavelength in one of them. So you just gotta know what variables you have and see what formulas you you should use. So that's just important to know. And here's example 1. Calculate the wavelength of yellow light emitted by a sodium lamp if frequency of the radiation is 5.1 times 10 to the 14th hertz. And so we have to choose what formula we have, and luckily it gives it to us. So if you didn't know which formula to use between the two, you have to first look at what you need. So you need wavelength, a formula with wavelength, and luckily there's only one with wavelength. The other one doesn't have wavelength in it. So if you ever see wavelength, it's always this first formula, C equals wavelength times frequency. And so first we got to set up the formula. So 3 times 10 to the 8th equals, this is just given to us because the constant, equals wavelength, or I would just call it x to make it easy, and then 5.1 times 10 to the 14th, and pretty much you just divide this, the speed of light, divided by the frequency, and you just put these in parentheses and enter into your calculator and get 5.88 times 10 to the negative 7th, and it's in meters because this formula just gives it in meters. And example 2, calculate the frequency of blue light with a wavelength of 6.05 times 10 to the negative 7th meters. And so it's this formula again because we need frequency and we have wavelength, so we need to use this formula because it has both of these variables. And so the c, which is the speed of light, is given to us, and wavelength, in this case it's in the problem right here, so you just plug it in, and then v you can just treat as x. And so to isolate x, we need to divide this by this. So 3 times 10 to the 8th divided by 6.05 times 10 to the negative 7th, and we get 4.96 times 10 to the 14th s to the negative 1. In example 3, calculate the energy of the yellow light emitted by a sodium lamp if frequency of the radiation is 5.1 times 10 to the 14th. The first time I saw this problem, I thought it was the same exact problem, but this one is calculate the energy. So once you see energy, you know it's a second type of formula because this is the only formula of the two to have energy. So if you see energy, just go directly to this formula. And if you have frequency. And so E will be your x this time, and h is Planck's constant, which is 6.63 times 10 to the negative 34th, and then v is given in the problem. So we just multiply these two numbers together and we get energy. It's just a simple plug and chug. And so it's 3.38 times 10 to the negative 19th joules, because energy is always in joules. And example 4, calculate the energy of blue light with a wavelength of 6.05 times 10 to the negative 7th. And this problem is a trick question because you technically need both formulas this time, because we have energy, but we are given wavelength. So we first have to calculate the frequency, and then we can go to the second formula. And so, first we have to calculate the frequency, which is V, if we have this. And so, we have C is given to us. So you just plug in C. And we have the wavelength. So we plug in wavelength for this thing. And we need frequency, so we divide this by this. And we get V, and so which is 4.96 times 10 to the 14th. And now we can go to the second formula with the E and find energy. So we have V, and second formula right there. H is Planck's constant, which is always given to us, 6.63 times 10 to the negative 34th, times 4.96 times 10 to the 14th, which we got from the last problem, or from the other formula. And we multiply them and get energy, which is 3.29 times 10 to the negative 19th. So here's a quick quiz to see what we learned. And so, which of the following relationships is true? High energy light has a higher frequency than low energy light. B. High energy light has a longer wavelength than low energy light. C. High energy light travels at a faster speed than low energy light. Or D. High frequency light travels at a slower speed than low energy light does. And so if you remember, speed of light is always the same for all types of radiation. So you can eliminate C and D because they talk about changing of the speed of light, which never changes. Speed of light never ever changes. And so if once you see that, you can immediately eliminate them. And then let's look at B. High energy light has a longer wavelength than low energy light. Does that sound true to you? Well, this isn't true because high energy light, like gamma rays, has those little tiny squiggles, and those barely have a wavelength at all. So the answer is A. High energy light does in fact have a higher frequency. So the more frequent the wave passes through, the more energy it has. And so the energy of EM radiation is greatest for A. visible light, B. ultraviolet light, C. infrared light, or D. X-ray radiation. So if you recall your little mnemonic, rabbits meet in very unusual, expensive gardens. So radio waves, M is for microwaves, I is for infrared, V is for visible, U is for ultraviolet, X or expensive is for X-rays, and G is for gamma. So gamma is the greatest, but what's the next greatest is X-rays. So X-rays the most energized radiation out of all of these, and so the answer is D. The longer the wavelength of the light, the A higher the frequency, B higher the energy, C lower the frequency, or D lower the energy. Well, if you remember just a brief sketch of the electromagnetic spectrum, radio waves are on the left side, and they have the long waves. And if you remember, radio waves are the weakest. And so the longer the wavelength of light, the lower the energy. That's definitely true. And if you remember, the longer the wavelength, the less the frequency, because these waves are so long, it takes so much time for them to pass through. So it is also lower the frequency. So C and D are correct. And that is the end of today's lesson. I hope that helped you learn about the electromagnetic spectrum and the atomic emission spectrum. If you have any questions, please ask your teachers. The next few videos will be continuing with Unit 3. And I hope you have a good day, and we'll see you later.